So these notes are going to be on exponential growth and decay. So for the first blank, a function grows at a rate proportional to itself. So the differential equation is dy dt equals ky. So we're saying we're looking at how y changes in relationship to how the time changes, right? So k is going to be our proportionality constant. Which is our relative growth rate. So we have three things that could happen. We have that k could be greater than 0, which would mean that we're talking about growth. We have that k could be less than 0, which would mean we're talking about a decay problem. Or we have that k could equal 0, in which case we would have no growth, no decay, it would just be constant. And then the other thing we have to define is dy dt, and I already kind of explained it using math terms, but in the context of this situation, we're going to say that that is the rate of change or the rate of growth. So if we're going to find the function that is a solution for that differential equation, then we can go ahead and start off with our differential equation dy dt equals ky. And then as you guys recall, we want to have our variables on opposite sides. We want to separate those. So I'm going to divide this by y, and that's going to give me 1 over y dy equals k dt. So here, remember, k is not a variable, it's a constant, and so we're thinking of the k as being on the side that would have the t's with it. So now I can go ahead and integrate the left side of the equation and the right side of the equation. So that gives me ln y equals kt plus c. So anytime I have a constant, when I find the antiderivative of that, that would have just been that constant multiplied by the variable. So now for me to find the function, I just have to solve this equation for y. I have to get that alone. So to undo the ln, I'm going to go ahead and put the e on each side. And I have y equals e to the kt plus c. And if you guys recall, we have another way of writing that, we can think of that as being e to the kt times e to the c. So that's what you would have if you had two exponents being added together like that. It means you have the same base being multiplied. And so this whole thing would represent one constant. So I'm going to say y equals c e to the kt. So now I want to think about what would happen if I was to plug 0 into this equation. So if I said y of 0, that would give me ce to the k times 0, because t is the variable I would plug it into. That's the independent variable. K times 0 is 0, and so you have e to the 0, which is 1. So if I plug 0 into the equation, I get c times 1, or just c. And that means that this c right here is the initial value. So that c right there is the initial value. Okay, so here are some examples, or this is going to be our first example. We have the population of bacteria grows at a rate proportional to itself, and so that's them telling us that we're going to be using this type of formula. Initially, there were 50 cells of bacteria. 2 hours later, there were 125 cells, and it wants us to find the amount of bacteria after 8 hours. So I'm going to go ahead and start off saying that this is the equation that I'm using. I know that my initial value is 50, And I know that 2 hours later there's 125 cells. So I know that at 2 hours there's 125 cells. So that's my t value, that's my y value. So I'm going to go ahead and start off just saying, all right, I know that this equation is 50e to the kt. And now I want to use this other information that I have, this other point, to figure out what this constant is right here. So I'm going to say 125 equals 50e to the k times 2. And then I'm going to get to where I can solve that for k. So I'm going to start moving things away from the k. So I'll go ahead and divide by 50. And that is 5 over 2, or 2.5. I'm going to go ahead and leave it as 5 over 2 equals e to the 2k. And then for me to get the k isolated, I'm going to ln each side. So I'm going to say ln of 5 over 2 equals ln of e. And those cancel, so that equals 2k. And then I'm going to go ahead and divide by 2. So I'm going to say that k equals ln of 5 halves over 2. So now I know that if I'm looking at this equation specifically, I'm going to say y equals 50e, and then my k was that whole mess. There's my equation right there. So now they want us to find the amount of bacteria after 8 hours. So that means I'm going to be taking this equation right here, and I'm plugging 8 in for t. So I'm going to say y of 8 for my 8 hours is 50e times ln of 5 over 2 divided by 2 multiplied by 8. So I went ahead and typed that in exactly the way it looks. And I got 1,953.125. So I'm going to say after 8 hours, there will be about that many bacteria. So remember, anytime we have a story problem, we should have a story answer. I do want to see full sentences on problems like that. Okay. If you look at the next page of your notes, now we're going to talk about half-life problems. So you guys have seen these before. We are actually going to do the half-life problem using the same formula that we used before, the CE to the KT, and I'm going to show you guys how that works. So if you recall, half-life means the time required for 1/2 of the quantity to decay. So if you said the half-life of carbon something, whatever number, was 500 years, and you started off with 100 grams, then in 500 years you would have 50 grams, and in 500 more years you would have 25 grams, and then in 500 more years you'd have 12.5 grams. So that's what it means by half-life. So we're going to say that we are using y equals CE to the KT. We're still going to use that. So for this example, it says the half-life of radium-226 is 1,590 years. A sample of radium-226 has a mass of 100 milligrams. Find a formula for mass after t years. So that means that we're going to have to not only know what C is, we're also going to have to know what K is for us to know what that formula is. And then find the mass after 1,000 years. And then when will the mass be reduced to 30 milligrams? So they're actually asking us for quite a few things here. So we're going to go ahead and start writing the equation. We have y equals CE to the KT. And we know that the initial value is 100, so y equals 100 e to the kt. Since we're doing the half-life formula, we know that the y value is going to be 50 after one of the half-lives has happened. So after 1,590 years, we know that we're going to have 50 milligrams left over. And I know that because that's what half-life means. So I'm going to go ahead and get to where I can solve for k. So this is the part where I'm just trying to figure out what the equation is in terms of t. I need to have a number for c and a number for k. I know that my initial value is 100, so I know that's going to be in the equation, but right now I have to figure out what that k value is to make this work. So I'm going to divide the 100 over, and I get 1/2 equals e to the k times 1,590. And when you do half-life, this will always happen. You'll always have 1/2 when a half-life has occurred. And then we'll go ahead and ln each side. So we're going to say ln of 1/2 equals 1,590k, and then we can divide by that 1,590. So the formula in terms of t is 100e to the ln of 1/2 divided by 1,590 times t. Now, there is a little bit of simplifying we can do here, so I just want to walk through this in case you are in a situation where you see multiple choice answers and you want to know where some other answer came from. So I'm going to go ahead and do this in red so that you guys can differentiate between the two. 1/2 can be written as 2 to the negative 1 power. So I'm going to take this ln of 1/2 and think of that as 2 to the negative 1 power in there. And then if you guys recall the way that the properties of logs work, if you remember, anytime you have an exponent, you can actually just move it to the front. So we could say that's negative ln of 2 divided by 1,590. So an alternate answer for this would be negative ln 2 divided by 1,590 with a t right there. Two different answers, both of them are mathematically correct. I just wanted you guys to be able to see that these two really are the same thing, even though it looks like they're not at all. Okay, so next we want to answer the second question in there, which was find the mass after 1,000 years. So I'm going to say y equals 100 e to the ln of 1/2, or you could use the other one if you wanted, times 1,000. And that is 64.666, it looks like. And this is the mass, that's milligrams. So we're going to say after 1,000 years, there will be about there will be about 64.666 milligrams of radium-226. Okay. Last, when will the mass be reduced to 30 milligrams? So now we're going to go ahead and just say we have 100 e to the ln of 1/2. And that's going to equal 30 milligrams. And then we want to solve for that t, so we're going to do that same process that we did when we solved for k. We're just going to solve for t instead. So we have 3/10 equals e to all this stuff that I'm getting sick of writing. And we can go ahead and ln each side. So ln of 3/10 equals ln of 1/2 over that, 1,590 times t. And then I'm going to go ahead and divide by that value. And I got 2,761.775 years. So it will take about that long for there to be 30 milligrams of radium-226 remaining. And go ahead and write that sentence at the bottom, and we'll look at it tomorrow.